Hello everyone, today we'll be discussing Norton's theorem and maximum power transfer. So Norton's theorem is closely related to Thevenin's theorem, and the idea here is that instead of representing a circuit with a voltage source and a resistance in series with it, we could also represent it with a current source as a Norton resistance in series, in parallel with it. Now, as we'll see in the next slides, these two theorems are very, very close to each other, and you can go from one to the other. Now, what's important is the Norton resistance is identical, or exactly the same as the Thevenin resistance. So there is no need to recalculate that if you're going from one to the other. And the Norton current is determined by shorting the two terminals that you're interested in and finding the current that flows between those two terminals. After you do that, you can easily find the Norton's equivalence. So basically you would do the same thing as you would do for finding the Thevenin resistance, which is by turning off all independent sources and finding the resistance looking into terminal A and B, and then shorting the terminals A and B and finding the current that flows from A to B. So as you can see, they're very, very much similar to each other, and basically you can easily determine that this relationship holds based on the source transformation. So if you remember source transformation, we applied basically to Thevenin's theorem, we actually find the Norton theorem. So the relationship between Norton current and the Thevenin voltage is basically given by I is equal to VTH divided by N. So if you find the Thevenin equivalence, you can easily find the Norton equivalence. And so that can be something you could do if you're trying to solve problems. If you're asked to find a Thevenin equivalence and you feel more comfortable finding Norton equivalence, then you could do so. And vice versa, if you feel like you're more comfortable finding the Thevenin equivalence, you could find the Thevenin equivalence and then easily from there find the Norton equivalence. So as we mentioned, the ideas are the same. RTH is going to be equal to Rn. You would find the open circuit voltage to find the Thevenin equivalence, and you would find the short circuit current to find the Norton equivalence. And you have to turn off all the independent sources to find the equivalent resistance, as we mentioned before. If you do have a dependent source there, though, you do not turn it off. You leave it as is, and then you have to use a test voltage to try to determine what the resistance or equivalent resistance of the circuit is. We'll solve some problems in class related to this, but we'd like to transfer to the new topic, which is maximum power transfer. So obviously what we have is we mentioned that when we have these equivalent circuits, the Thevenin or the Norton, what we would like to know is what load would give us the maximum power transfer from that circuit. And so we will look at this. But overall, so if we look at the Thevenin equivalent circuit here in this figure, if we connect a load resistance across the terminals A and B, the real question is what should be RL for us to achieve maximum power transfer. So if we look at what is the power transfer at RL, it's given by VTH divided by RTH plus RL. So this is I. We square it because that's I squared times R will give you the power that is dissipated from the resistance. So basically the maximum power that is transferred to RL is given by this expression. If we plot it, what we'll notice is that the maximum power transfer happens when RL is actually equal to RTH, the Thevenin resistance. So that's when you achieve maximum power transfer. Obviously, as you deviate from these values, you reduce the power transfer. So if you go RL to equal to infinity, obviously you have zero power transfer, and as you go RL equal to zero, you have again zero power transfer. So Thevenin and Norton equivalent circuits are very helpful in trying to understand the behavior of realistic sources. So as you know, ideal voltage sources have no internal resistance, and ideal current sources have infinite internal resistance that is in parallel. So in the case of voltage sources, you have no resistance in series, and in the case of ideal current sources, you have maximum or infinite resistance in parallel. And so the Thevenin and Norton circuits actually show deviations, right? Because if we were looking at the ideal scenario, we would have a voltage source in series with no resistance there and connected to terminals A and B. But in the Thevenin case, we have the voltage source and its resistance is in series. So we're really looking at a non-ideal voltage source, or when you're looking at a Norton equivalent circuit, you're looking at a non-ideal current source. So what's very interesting is that when you look at the Thevenin circuit with a load resistance, when you add the load resistance, the internal resistance works as a voltage divider. Now the lower the load resistance, the more of the voltage drop actually occurs across the source. So it's very important that we understand that as we reduce the value of this, obviously more of the voltage drop happens to be across RS, and so what we have is that we're getting closer and closer to that VL that we are of it that we expect to receive we were getting closer and closer to VS, which is what we anticipated to receive from this voltage source. So what that means is as load resistance increases, the voltage source comes to behave closer and closer to operating like an ideal source. And this is very important because, as I mentioned before, if you connect a load that has a very low resistance between, for example, a battery or any sort of power source, you would see significant voltage drop from the voltage that you would expect it. So for example, if you have a car battery that is supposed to supply 12 volts, when you connect that to a load that has very little resistance, that 12 volts could be down to 6 volts. So this is very important for example, starting up your car in the morning. Generally speaking, batteries, the voltage actually drops in the cold. So when you go to start up your battery in your car in the cold, your starter motor uses the most amount of power almost compared to anything else in your car. And when you try to crank the starter motor when it's very cold, the voltage for the battery is already low. But now you're connecting a load to the battery that has a very low internal resistance. That brings the voltage even further down. And so you could run into a scenario that your car will not start. And that's why you need a very good battery to be able to start your car in very cold conditions. And similarly, we could look at a current source. If we are looking at a current source, the lower the resistance of the load, the more of the current is actually flowing through the load. So when we're approaching the scenario where the load resistance is actually equal to 0 volts, we are approaching the scenario where we're getting closer and closer to an ideal voltage source. Current source, sorry. And as you can see, again, we can see this practical scenario as we increase the load resistance, more and more of the current is actually flowing into here, and we're not seeing that IS. But as the low resistance is very low, we're getting very, very close to seeing that IS actually flow through the load. So there's a difference there, right? So for a current source, we would like to have the smallest value of the load to see that maximum current flowing through the load. But when we're looking at a voltage source, we would like a very large resistance to get closer and closer to that ideal behavior. Obviously, in a lot of cases, when you're looking at outside world, you're looking at voltage sources, right? Your outlets are voltage sources, your batteries are all voltage sources. Current sources are mainly, as I mentioned before, happens in the case of transistors. Now, we could use this concept to try to actually measure resistance. Obviously, you can measure resistance using multimeter, and I brought my multimeter to class, and we were able to look at this. However, there is another way we could do this, and that's using a Wheatstone bridge, which I discussed before. So if you have 3 resistances where you know the value, R2, R1, and R3, and yet one of them has to be variable. If you put a galvanometer, which is a very, very sensitive current meter, in between these 2 terminals, and then you connect your resistance that you don't know across these 2 terminals, then you can adjust the resistance R2 until there is no current flowing across the galvanometer. That means that now this point and this point have the same potential, and the electrons have no incentive to move from here to there. At that point, the relationship that dictates the value of Rx is given by Rx is equal to R3 divided by R1 times R2. So now you could actually find the value of Rx that you didn't know. Now, why is this a very accurate method? Because even the smallest amount of voltage difference would result in a current flowing between the two terminals, and the galvanometer will pick that. So this is a very accurate way to try to determine the voltage across, determine the unknown resistance. With that said, we come to the end of this lecture. Thank you.